3:30. Okay, hello everybody. It's 3:30, so we will begin. First, as a starter, those of you who are on site, could you please make sure you use the on-site tool so your attendance is registered in the blue sheets. And thanks for all those who are attending remotely as well. We do need a minutes taker. Does anybody want to volunteer to take minutes in the Etherpad? There's closed captions in this meeting that can help. Do we have a volunteer in the room? If not, we'll just transcribe from the closed captions. But if a volunteer appears by the end of the... No. Oh, sorry. I'm told to be louder. Yes, so I'll just repeat the question. Is there a volunteer to be a minutes taker? And the Etherpad tool. No. Okay, I guess we'll just try the experimental. Oh, there you go. Thanks a lot. We'll check in later. Okay, so first I'll go through the usual agenda bashing. Welcome everybody to the Quantum Internet Research Group meeting. We have 1.5 hours. As usual, the first note is the note well. Going to leave it up on the screen, but basically IETF follows IETF intellectual property disclosure rules. The meeting is recorded. Follow the links for privacy and code of conduct. And the usual reminder that we are part of the IETF. We are not a research group. We are not a standards development organization. We're here to foster research. Okay, and with that done, let's a final reminder that the session is being recorded and there's an on-site tool. There's a QR code on the screen for those of you who are on site. And please keep your mask on unless you're speaking to the microphone. Right, so let's begin with the Quantum Internet Research Group meeting at the IETF116. So first, we're going to quickly go through the agenda for today. It's a pretty packed meeting today. We're going to start with the 5 minutes of agenda bashing. We're going to spend then bulk of the meeting having 3 talks about the testbed networks around the world. Then we're going to have an update from Melchior about the use case draft. And we're going to conclude with Carlos' talk on experimental demonstration of entanglement delivery using a quantum network stack. And at the end, Rod will announce a book. And so we only have actually one update as an RG. It's that the architectural principles draft is actually now RFC 9340. So a great success of the group. Yeah. And the use case document still in progress, and we'll be discussing it today. Okay, with that, I would like to now hand over to our first speaker. Jesse, are you online? Do you know which button to press to share your screen? Hi, Jesse, can you hear us? He's online. Hello. Hi, yes, are you online? Can you hear us? there's some...
Switch to Joaquin first?
in a second, because if Jesse can't do it now, he'll have to go.
That's right. You said they have a time
Yeah.
issue.
Oh, I think he's trying to reconnect. Apologies for the issues. We'll give it 2 minutes if... Oh, yes, is back online. I can... Hi, yes, are you able to use your mic? I can share slides for you if the screen sharing doesn't work.
No reply from them. All right, it's 7 after. We might have to move on.
Okay, let's... guess we'll have to move on. Joaquin, are you there?
Wojciech in, yes, here.
Yes, can you hear me?
Oh, yes, sir, you're there. I can hear you. Great. Should I share your slides, or will you be able to share your slides?
Please do. That's maybe easier. If you
Okay,
share.
I'll share the slides. You just have to let me know when to hit next slide. Otherwise, go ahead. And if you could make yourself a bit louder.
Yeah, I will do. I hope it's better like this.
Yeah, a bit better. Thanks. Go ahead. You've got 20 minutes.
Great. So good morning, everyone, and sorry for my delay. Need to log in. So thank you for having me on this meeting, and was asked by Wojciech to present a couple of developments on the testbed activities that we're doing in the Netherlands. And I will give you a short overview what we are doing, and maybe there are some questions at the end. So moving with the introduction of myself on the second slide, I'm one of the Quantum Delta leads, and Quantum Delta is a foundation to accelerate quantum technology in the Dutch market and in collaboration with many other players globally. So I'm one of the co-founders and lead of the CAR2 program that is about quantum networking and coordinating all the activities on this in the Netherlands and abroad. I come later back on this. I have a long background in digital infrastructure, worked previously for KPN, where I was one of the founders of the IPTV product of KPN, was a technical director for Ericsson Broadcast and Media Services, and one of the chief commercial officers of the Amsterdam Internet Exchange, which is one of the biggest global peering points in Europe. And I have an affiliation with TNO, the National Research Organization in the Netherlands, and I'm one of the advisors of EuroHPC, where also quantum computing is part of it. Then on the next slide, I will present about Quantum Delta, what we're doing there. It's good to have this as an introduction. In the Netherlands, we built up since 2019 a large program to accelerate quantum technology in the Dutch market around quantum computing, quantum networking, and quantum sensing, with the goal to accelerate all these developments that already were happening the upcoming years. And we have been awarded by the Dutch government and funding from other players to work on this and to work the coming 5 to 7 years and make that happen. It's not only about the development of the technology. It's also about how can we apply and set up new research in quantum fields. How can we build the ecosystem around startups, tech transfers, community building. It's also about training the workforce for the future, because we think quantum is, of course, important. It will be big, and therefore we need more people from the academical institutes, but we also need the hands from other institutes to build the machines, the hardware, and the software engineering. And not to forget, what is the impact on quantum technology on the ethics and all the other discussions about society and the new technology. And we have also invested in the National Clean Room infrastructure in the Netherlands, because not only for the nano environment or the photonic area, also for the quantum area, there is a good clean room infrastructure required to develop the technology and everything around it. Moving on to the next slide. This foundation was set up by leading institutes in the quantum area, mainly concentrated in the Delft area around QTech, which is a collaboration between the TU Delft and the Applied Research Organization TNO, around QSoft, a quantum focus area in the Amsterdam area, focusing on quantum applications and algorithms. And this institute is driven by the University of Amsterdam and the Center of Mathematics. And then in the Eindhoven area and in the eastern part of the Netherlands, the Twente area, there's a lot of developments on quantum connected to photonics and nanotechnology. And all these institutes started to collaborate together and drive that agenda of quantum technology with the Quantum Delta Foundation. So this as an introduction, and I'm moving now on to what's happening in the quantum networking field. Moving on to the next slide. There's a lot of things happening in the Netherlands around quantum technology. And I think this slide is not that well working in this setup of presentation in Meet Techno, but it would have proposed an overview of what's happening on quantum technology in the Netherlands, and that was also published in the media. Like the development of the first quantum link in 2015 on the campus of the University of Delft in Delft, of course. The setup of the Quantum Internet Alliance, where the Netherlands is driving this alliance in the Netherlands to come to repeated technology, memories, standardization, and many more, to the first entanglement links and the developments around teleportation, technologies in the quantum networking field that are driven in the Netherlands and where we have a lot of cooperation on global level. Then if you move on to the next slide. As mentioned in the introduction of Quantum Delta, we're working on a national program, and in that program, the development of quantum network technology is important in this area. So also in this program, we have the goal to strengthen developments of quantum networking in general and quantum internet technology. The goal also to build a national network to connect the different quantum locations with the first generation of quantum network technology. To link potential users to it from the academical world, from the telecom infrastructure, but also from the end user perspective. That could be from a governmental area or from a banking area or other industries that wants to work with quantum network technology and wants to do some experience on it. The national testbed will be also positioned to do something with the cloud infrastructure, mobile networking, and of course, the development around software applications and security, and connect everything around it. Then on the next slide, we have the focus on where we're working on. At the moment, there are two important developments going on in the Netherlands. First, of course, the focus is to work on quantum network technology or quantum internet technology to connect quantum computers or quantum processes on the longer term. And as a spin out of these developments or as a first transfer of this technology, we have the first generation quantum technology available, also called the quantum key distribution technology. And therefore, we have already the first spin outs in the Netherlands. And the main activity there with quantum key distribution technology is to protect the data streams on a classical network, exchange the keys on a quantum network, but again, with the encryptors, provide a solution on the classical infrastructure that is out there. And that's the two directions that we're moving on at the moment. Moving up to the next slide. So the main goals of the quantum program in the Netherlands, if it comes to quantum networking, is build that fundament for a national network, set up different test beds and showcases. Will come later on in this presentation, focusing on the hardware and software developments, and not to forget the standardization. And that's also the link to this event that I'm now presenting on. Especially around the hardware development, there's a lot of things going on, also on the fundamental part, but also more and more on the applied side and on the productized side, and the software focus becoming more and more important. And I think also is important for the end user perspective. And develop a couple of use case and applications, and position the Netherlands on this level on different international developments around quantum networking and quantum internet. In Europe, there's a development to build up quantum networks driven by the European Commission. QTech is leading the Horizon program called the Quantum Internet Alliance. So there's a lot of things going on that will accelerate the developments from the Netherlands in cooperations with many partners on global level. Moving to the next slide. Then the goal of the K2 program is split in three. We have a couple of test networks, R&D networks running in the Eindhoven area and in the Delft area. That was first starting with development in the Delft area to test and to experiment with the QKD technology. And now we are working with that same network on the quantum internet technology. And in the Eindhoven area, the R&D technology is built up to test in different use cases and different end user solutions. And the goal is really to drive these developments on these R&D networks. And if it's becoming a bit more mature, in the end, transfer it to a staging network, the phase 3. The staging network is a goal to build up a national network between these different locations, and there make a sort of stable environment where you connect other technologies or other application zones and play with the other applications and technology on that stable test bed called the NL Quantum Staging Network. And if we are successful there, and then we have the goal to transfer it to, we call the quantum network construction support, where industries that are interested to work with quantum network technology, we can provide with information, with experience, but also if they're starting with working on quantum network technology, we can loop the experience back from the industry to the developments on a stable network called the quantum staging network. And even from there, if it's required that there are some technology failures there, loop it back to the R&D developments there. So a program that is set up with different phases, scattered also over different years. At the moment, the main part is on the R&D networks. The upcoming 2 years, we transferred it to the developments around the staging network, and the follow-up will be spread it out to the industry and loop things back. We're moving up to the next slide. So the main goal is then that national quantum staging network, as I explained, as said in the Delft area, and I hope you can see it. There are small yellow lines where we have different connections from the Delft to the city of Delft, the campus area of the TU Delft, to The Hague, where we have a big important telecom hub there. And in Eindhoven, there are different R&D connections at the moment to the automotive campus and to the smart housing campus, where we can project data streams to these different areas. And then the upcoming years, we will start building up the connections between the main cities, the main hubs, Eindhoven, Delft, Leiden, Amsterdam, and maybe more to develop and build that stable network. Moving on to the next slide. Then one of the cases that we start working on in the Eindhoven area is how can we protect the data streams from and to a base station of a mobile network that is connected, for instance, to a 5 or 6G network, and that's even connected to a self-driving car, because you would avoid that a data stream to a mobile self-driving car could be hacked and someone is taking over the steer remotely over. One of the cases that we will work on the program. Then the next slide. And then in Eindhoven, also they're working on a sort of technology agnostic test bed, where there are different connections planned already under construction at the moment from the university campus of the TU Eindhoven to different test environments. Like I mentioned, the automotive campus in Helmond and the smart housing environment in Waalre, but also connecting to the smart industry environment there. The goal is there to build up these different networks, but keep in mind that it is technology agnostic, that you can play with different QKD developments there, test it, how that could work, and how can we make it applicable for different types of industries. So we are flexible there to work with technology, but also with different industries and build up the experience on these different solutions and end user applications. Next slide. And then moving much more to the QKD and the IQKD developments that are going on in the Netherlands, especially in the Delft area. The TU Eindhoven QTech, cooperated with Tino, has worked for a couple of years on the development of MDI QKD, where there is a center node and different distributed nodes that connect to that center node, and where you can exchange the different keys from that center node or by that center node to the other locations there. The development was mainly driven from QTech, has said, and was tested in 2021 on the KPN network, or an R&D part of the KPN network in live environment. And there we have shown that we really can protect with this technology different video streams from one to another side on a classical network that was also bundled with the MDI QKD technology. The MDI QKD technology is, compare other countries, we are just one of the players at the moment in this field in the Netherlands. QTech was one of the first developers in this direction. We know that in China things are going on this field, but at the moment most visible and most applied is what's happening at the moment in the QTech area in cooperation at that time with KPN. Then on the next slide, we made a next step to Eurofiber. Eurofiber is also one of the biggest fiber operators in the Netherlands, with connectivity all over the place, connecting all the mobile networks of Vodafone. We also have a lot of cross-border networks to Germany, France, Belgium, and Luxembourg. There we build up again the MDI QKD technology from different operational data centers, where we connect 3 locations at the moment in the center part of the Netherlands in cooperation with Juniper. Also from the MDI QKD developments, there was a spin out at the moment that's called QBird, and they are commercializing and productizing the MDI QKD technology at the moment. The difference compare the previous setup in the KPN environment is this is really in data centers that are fully operational, that are hosting also many other critical parts of the infrastructure, and that the fiber that was used also was bundled with data from other operational environments there. So this was set up in a complete open environment from Eurofiber, and also customers of Eurofiber are able to work and trigger and test solutions on this test bed in the Utrecht area. Moving on to the next slide. Important is also good to understand that in Europe there is a big push from the European Commission at the moment to build up national quantum network infrastructure at the moment. So a couple of years ago, the European Commission set up the EuroQCI initiative with the goal to accelerate the quantum network developments in the member states. And last year, all the 27 member states were able to build a proposal to build their first quantum networks in the particular European countries that are part of the EU. And that resulted in 27 proposals where there were a difference in maturity and experience, especially in countries like the Netherlands, in Spain, in Italy. There's a lot of developments around quantum networking and QKD technology there. So they built more advanced proposals than in other countries, but smaller countries or bigger countries that didn't have that much experience in development of quantum network technology, they're working close together at the moment with other member states that are more experienced in this field. And the goal is to build these national networks there, but as a follow-up, the European Commission will start pushing to build up cross-border developments between the different member states. So an important initiative that's also a bit pushed by the European Commission to focus on the sovereignty developments in Europe, so that there will be an industry build up, an experience build up on this technology within Europe. This is one of the big developments if it comes to the first generation quantum technology, but also there are developments that are linked to the Quantum Internet Alliance to build up quantum internet technology that is funded from the Quantum Flagship. And then not to forget, there's a lot of things going on around quantum technology in Euro H2C to accelerate the supercomputer infrastructure with quantum computing technology, but also connectivity will be very important. And then not to forget the discussions about CHIPS Act, where also quantum has a prominent place and could affect the quantum network technology developments. Moving on to the next slide.
Yes, I'd just like to know, you have 1 minute left.
Okay, I will do my best. From this translation to a European project in the Netherlands, we have started to build up 3 important networks there. A QPD technology that is focusing on connecting and protecting the data streams in a governmental area where different ministries of the Netherlands are involved and see how that could impact their security level in their environment. Accelerate the technology agnostic testbed in the Eindhoven area, and building up again a testbed in the centralized part of the Netherlands to focus on the elements that needs to be a development for a national network. Then as a closing remark, maybe Wojciech, you could skip to slide 23. So there were a couple of slides in between, but I think the majority of the focus that we're doing at the moment in the Netherlands about quantum testbed developments, I think was summarized in this introduction. At the moment, we have a strong focus at the moment on not only do this standalone in the Netherlands, but also work close together. So the main goal is to drive these R&D networks and translate it to stable and focused testbeds as prepared and presented earlier. Focus on building that national quantum staging network, show the leadership of this tech development in Europe, work close with other countries in Europe, but also global, and accelerate these developments, and see how we can accelerate also the connections with neighboring countries, not only in the Netherlands, but also not only in Europe, but also broader. There's a lot of developments also going on satellite communication, which is not in our program, but is important to work close together and build up a new partnership and drive this ecosystem. One final sentence about the link to this event. It's good that we are aware, that you also got aware of what's happening on this field. Standardization is, in my opinion, really crucial to drive these technology further at the moment. Although globally we have some challenges in geopolitical challenges, everyone is always able to keep the internet up and running despite of all the political challenges that we have. And that's also required in this development. And I think standardization could drive these developments to connect and work close together in this field. Hope you have a good overview of this. Thank you for your time and have a great event.
Thanks, Jesse. Let's keep the questions until all the testbed talks are done then. Thanks, Jesse.
Right.
Joaquin, can you try sharing your screen?
Yeah, let me try. I put a request for sharing the screen.
Should be coming out. There we go.
All right.
Okay, go ahead. You have 20 minutes.
And make sure, tell him to make sure he speaks loud.
Oh, and please speak loud.
Sorry, can you hear me clear?
Now, yes, we can hear you now.
Okay, thanks. Yeah, thanks for having me. Let me go one slide back here. So yes, my name is Joaquin Chung. I'm a research scientist at the University of Chicago with a joint appointment at Argonne National Lab. And today I'm gonna present the design and implementation of the Illinois Express Quantum Metropolitan Area Network. Um, I'm gonna try to go through the slides in 15 minutes, and if there is questions, I can address them in the rest of the time I have. So the Illinois Express Quantum Network, or ICNet, as we like to call it, because of Isaac, the nickname Ike, is a program to realize metropolitan scale quantum networking over deployed optical fiber using currently available technology. This is a collaboration between two national labs, with Fermilab as the lead and Argonne National Lab as a partner, two universities, Caltech and the University of Northwestern University, and two industry partners, Hyperlight and Nucrypt. So all this talk is based on this recent publication. Let me turn on my laser pointer here. That was published in the Transactions on Quantum Engineering uh, last year. So the motivation for developing IGNet, it was to develop a quantum metropolitan area network, and I say circa 2019 because that's when the project was proposed and funded. So when we saw back in the day, most of the networking demonstrations were focusing on just point-to-point or linear topologies. So um, we saw that there was a great need to develop architecture for fully dynamic and automated quantum networks using existing technologies to demonstrate multi-user, multi-node capabilities in metropolitan scales that go beyond linear topologies. So here I have illustrations of several point-to-point links, and recently an Oak Ridge National Lab demonstration of a three-node quantum local area network. But wait, breaking news. There is quantum network testbeds appearing around the world with Japan. We already learned about the Netherlands. There is also some in the UK, New York, Chicago. So with that, let me give you a brief overview of what is the IGNet topology. So here on the left, you can see our conceptual topology. So we have three sites, one at Fermilab that we call these sites quantum local area networks, or QLANs for short. So the Fermilab site will have we will have also the Northwestern and Starlight. Starlight is a quantum internet exchange point that aggregates fibers all over the world, mainly connecting Europe and Asia with the US. And then we also have a QLAN tree at Argonne. We envision to have these connected via a WDM ring at a metropolitan scale, and then each of them we have QLAN switches that are all optical passive switches, and different type of quantum nodes that we call Q nodes. So here in this map, you can see where are the QLANs located. We currently have a 50 kilometers dark fiber between Argonne and Fermilab. We have another fiber that is 83 kilometers long between Argonne and Starlight, and then a 22 kilometers long fiber between Starlight and Northwestern. And we are planning to connect Starlight and Fermilab in the future. And here in the inset are the two locations that we have at Fermilab campus. So what were our design considerations? As I mentioned at the beginning, we wanted to design a repeaterless transparent optical network in the Chicago metropolitan area to demonstrate quantum network capabilities beyond point-to-point communications. Our requirements were a coexistence between quantum and classical information in the same fibers, flexibility to incorporate components developed outside IETF, such as future quantum memories, and support for multi-node and multi-user operation. Our approach is to take a layer architecture with centralized control, inspired by software-defined networking. So we decouple the control and data planes, define several management functions such as routing and quantum channel assignment, dynamic optical path establishment, calibration, and optimization functions. And we use SDN to orchestrate all the all optical switches and multi-wavelength entanglement photon sources that we will have in the network. So this is the result of our architecture. Is a three-plane quantum network architecture. In the bottom plane, we have the quantum infrastructure plane, where we have all the devices. And here is an illustration of our topology with all the Q nodes and all optical switches, entangled photon sources, and Bell state measurement nodes. So then we have the control plane that we separate into sub-layers. The bottom layer is the device control functions, and it performs tasks such as error detection and feedback, quantum channel calibration and optimization, and time synchronization. And the upper layer of the control plane is the global view of the network, the one that we call network control functions. And it does the optical path routing and wavelength assignment and quantum network resource and topology discovery. And finally, on top of the control plane, we have the quantum network application plane. And at the moment, we are looking at very basic application services such as end-to-end entanglement distribution and quantum teleportation. So if we remember a paper from Stephanie Weiner's group, we can think of IETF as a stage 3 quantum network or an entanglement distribution network. So for the IETF control plane design, we have control and management functions, as I mentioned in the previous slide. Some of them are time synchronization of the remote location for distribution on entanglement, and they're used in subsequent applications. We will also have path routing and wavelength assignment because this is a repeaterless network. We need to create light paths between nodes, and because we say this is a multi-hop all optical network because we have several switches bridging in between dark fibers, and quantum calibration and optimization because we are dealing with single photon, and these when we encode qubits in single photons, they are very fragile, and the signals are extremely sensitive to noise in the quantum channels. So here on the right, I have a pseudocode of our shortest path routing wavelength assignment algorithm. Is really basic. The computer scientists in the audience will say, like, why are you showing me this? Because this is too basic. But it's just an example of the things that we're planning to deploy in the control plane. So for the quantum node, or Q node as we call them, these Q nodes are the communication parties in the network. And this diagram is just a cartoon. We will have three type of channels: a quantum channel that it will be sending qubits encoded in photons, and a classical channel for sending a fast forward control signals, and also clock synchronization signals. This doesn't have to be confused with an auxiliary data channel that is completely classical and is only for the control plane communications. So then in the quantum networking resources box that I have here, it contains all the quantum functions that a node can execute. Can go from EPS to Bell state measurement, and we expect all of them to have a single photon detectors for SNSPDs. And in the very top, we have the quantum applications that will initially include only, as I mentioned, entanglement distribution and quantum teleportation. So this brings me to the implementation of the control plane of so we have decided to use a centralized control framework composed of a web portal that will allow users to interact with IETF services, browse the topology, and monitor the status of their request. We will have a quantum or QNet server that manage all the control in the quantum network, manage all the resources, and provisions quantum network services. We will have an SDN agent that maintains optical network topology and set up and tear down the light paths. One example of the SDN controller that will sit below the SDN agent is ONOS. And all of the components of the control plane will communicate over a message bus. An example is MQTT, but we can use gRPC or anything else, even REST APIs. And then, yeah, you will see all these nodes here are the representation of the infrastructure plane. One example of a control protocol that we are planning to implement and is needed for IETF to work is the Quantum Network Resource and Discovery Protocol. I'm gonna go very quickly over the sequence diagram, but here is a pseudocode that you can also follow. Everything starts with all the Q nodes, EPS, and all optical switches loading their configuration at startup. Then the SDN agent will perform a topology discovery by querying all the optical switches using some SDN control protocol. It will build a topology. After that, all these Q nodes will initiate a registration that will happen in parallel. They will all register to the QNet server. After some time, the QNet server will have received so many registrations, and it will query the topology to the SDN agent, who will reply with the topology that independently it has built. So then the QNet server and the SDN agent will start a topology verification process in which the links that have been gathered by the SDN agent will be compared with the nodes that has registered, and QNet server will prune the nodes that are not online from the topology that the SDN agent built, and it will finally present a visualization in the web portal for the user. So now moving on to IETF demonstrators using the quantum infrastructure plane. Just to give you a feel of the resources that we have at IETF, at Fermilab, we are encoding qubits in time bins. We're using time bin qubits encoding. We have SNSPDs, entanglement photon sources, a clock source that is 5 picoseconds accurate. And we have a Polatis 16 by 16 all optical switch. At Argon, we have polarization entangled qubits. We have also an SNSPD from Quantum Opus, an EPS built by Nucrypt. We share the clock source from Fermilab for some experiments, but we also have a local one from Nucrypt. We have another 16 by 16 all optical switch, and these switches are from Polatis. If I'm allowed to make some promotion also for them. Then the node at Northwestern and Starlight, it's also using polarization entangled qubits. They have SNSPDs from different vendors, EPS also from different vendors. They have two Polatis 8x8 switches, both of them located at Starlight. So with that, this is one example of an experiment that was recently published in the Journal of Quantum Electronics of the IEEE, using the link between Fermilab and Argon. We were able to demonstrate a 3-node and 3-node, because we had two of them at Fermilab, using two pairs of 59 kilometers of fiber. So the 50 kilometers between the two national labs and some internal fiber going on. So we were able to demonstrate coexistence using photons in the C-band for the quantum channel, and a clock signal that we were sending both not simultaneously, but we tried both the O and L bands, and we were able to measure a car that when we were sending the entangled photons alone, we were getting a car of 51, but when we added the clock, it dropped to 5.3 over the 59 kilometers fiber. But this is still promising for enabling quantum communications. So for future work, I'm dividing it in the three planes that we have proposed for the infrastructure plane. We would like to demonstrate entanglement distribution between QLAN2 and QLAN3, so between Northwestern University and Starlight and Argon. We will implement conversion between time bin and polarization qubits and vice versa, so all the different QLANs can communicate between each other. And for the control plane, we will finish the prototype implementation of Q nodes, and then at the same time the AgNet controller, so we can demonstrate a running network. And for the application plane, we will demonstrate entanglement. We want to demonstrate entanglement distribution automatically controlled by the AgNet control plane and assisted by the Q nodes. So with that, I'd like to thank you for your attention, and I'll be happy to answer questions.
Thank you very much, Joaquin. Let's leave the questions for all the test beds until after the next speaker finishes, which is Shota Nagayama, who will talk about the Japanese test bed. Shota, you have 10 minutes because you're also speaking at the host series later this Thursday. So feel free to advertise that as well.
Are you on the?
Do you want me to share slides? I'm not in yet. I can just share your slides for you, and you just tell me next slide.
Yeah, let's do that.
Okay, well, I just shared between you the slides. So.
You get the old.
Oh, maybe I just. I'll just share.
And Joaquin, thanks for doing this at 2 a.m. Chicago time.
Just tell me when to move the slide.
No problem. It was a pleasure. Thanks for inviting me.
Okay, I have 10 minutes. So nice to meet you. So my name is Shota Nagayama. So I'm from WIDE project. So I believe I don't need to explain about WIDE project. And also I'm board member of WIDE project, and I'm a representative of a quantum internet task force. Can you go to the next slide? So yes, so today there are many projects all over the world to work on the quantum internet. So, but actually 5 years ago, so there wasn't, no quantum internet projects. So QIA started just after that. Anyway, so we started the researchers organization in Japan, Quantum Internet Task Force. So I talked to every quantum internet researcher in Japan. So most of them were physicists. So now more networking specialists are coming in, and Quantum Internet Task Force is led by the young researchers actually. So I'm the representative of that. And actually, so the senior researchers, so like professors, are the advisory members. And so our plan is actually doing quantum interconnect and the quantum internet is very related. So could you go to the next slide? Next slide, please. So yeah, this one. So our vision is so we want to make a world of quantum data. So like the today's world with digital data. So we want to connect all over the world with the quantum data. So like the quantum data can be at will generated and communicated and processed all over the world and everywhere. And so the quantum networks is useful for quantum interconnect of the large scale fault-tolerant quantum computers like this left side. And so I said I'm a representative of QITF, and also I'm doing a project manager of Japanese national project named Moonshot. So the Moonshot project is it targets the large scale fault-tolerant quantum computer, and many other there are 11 project managers and other managers working on the single quantum computers or theoretical things. And my mission is to achieve actual quantum network to achieve this kind of distributed quantum computer. And so our plan is first we will achieve this kind of quantum network for quantum interconnects, and we will expand that to quantum internet. So with that quantum internet, so we can connect more quantum computers over quantum internet. Also, we can transfer quantum data from quantum sensor network or other quantum networking tasks like security. Please go to the next. Okay, testbed plan in Japan. Okay, let's see. So in Tokyo area, so here is Kawasaki City. So next to Yokohama here, so there is a Kawasaki City, and Kawasaki City is a good place. So they are encouraging quantum technology these days, and we have a laboratory there now for our first quantum networking testbed. So our project has so many fields, so like quantum memory, quantum optical technologies, and quantum networking. So and also applications. So everything. So we will integrating everything here, and we'll achieve a quantum network. And actually, so the quantum memory is very hard technology to achieve, and it is hard to control too. So first, we will construct a 4-node star network with just quantum optical technologies, and we will. So this type of network, 4-node network, requires routing, and we will achieve so this kind of routing, maybe decentralized fashion. So you can read the technologies. The paper about such technologies from Rodman Media Group. And after that, so we will equip the quantum memories so into this testbed. And yeah, basically, this project is supported by the JST Moonshot project. So after that, so we will please go to the next slide. Expand that to data center level network. And then, so now please go to the next slide too. So then we will expand this to so Tokyo Asahi University campus and Yokohama National Universities. So this should be this will be the beginning of the Japanese quantum internet. So actually the internet today, so in Japan, it started from connecting Keio University and the University of Tokyo and the Tokyo Institute of Technology. So we will after that. So please go to the next slide. Okay, so this is just a kind of brief introduction of our presentation of the host speaker series. So this will be on Thursdays. So I and Rod Bamita will talk we'll talk about our effort more detailed. And lunch will be provided, so please be there. So maybe this is.
Let's thank Shota.
Thank you so much. So, one thing, so we are happy to contribute to the global quantum internet. One global quantum internet. So happy to collaborate. So please talk to us. So if we are interested, thank you so much.
Thanks, Shota. If you could stay there for a minute. If anybody has a burning question, we can have time for one question at the mic to all the speakers that have spoken so far. Okay. In that case, there's no live questions. Please remember that the participants are in the chat room, so you can always just engage them directly in the chat room for as long as the speakers are there. Thank you very much, Shota. Okay. And thanks all the other speakers, Yakin and Jesse. The next speaker will be the next part of the agenda is the use case drafts, and Melchior will be speaking about that remotely.
Hi guys, good day. Let me try to share my slides.
So laggy on sharing screens today.
Sorry, one moment, it doesn't let me share my screen.
It takes a few seconds to come up.
Right, now you should see it.
Okay, great. You have 10 minutes. Thanks, Melchior.
Yeah, I'll probably won't need the 10 minutes. So this is just a short update on the work we've been doing on the applications and use case drafts for the quantum internet. Basically, many of the comments, thanks to Rodney and Wojciech for the latest comments on version 13 and 14. We've addressed, we think, all the comments in the new version 15, which has been sent to the mailing list. And I will quickly go over them. And after that, we would like to ask for a research group last call. So to address the comments, many of the comments were, I think, textual, and some were more fundamental to the draft. For example, you can see we've removed, based on the comments, some claims, for example, mathematically proven to be unbreakable. When a quantum computer as a cloud service would become available. And we removed some wording, which indeed has been addressed earlier, and we've now removed them. Also some changes in the order, so moved entanglement down in section 4.1, and we removed again source destination from the figure. We moved the closing bracket, and replaced to transmit with to transfer in section 4.3. And Wojciech attended us or pointed us to a liaison document from ITU that addresses use cases for quantum internet as well. So we've added a section to refer to that document. I just found out, by the way, that the link which you now see on the slides doesn't work. So that would probably need an update in just this slide. But yeah, so with that, we think we've addressed all the concerns and comments. Again, thanks Wojciech and Rodney for extensive review and input. There were no other comments as far as we know on version 13 and 14. So we think the draft is quite stable. And we would like to hear from the working group if you agree, and from the chairs that version 15 is stable and can go for a research group last call. So it can go to IESG for consideration. And that's basically the update. Again, there weren't much other comments to address, so we think the work is pretty much done.
Yeah, Rob Van Meter speaking, just as an individual here. Thanks for the edits going on the draft. Most of my suggestions on that were all clarifications and wordsmithing, and I think you covered basically all of those. So it's been a couple of months since I looked at it, but given that you ticked those off, I think it's probably in pretty good shape. I think we're probably ready to get other people to take a look at it. That's just me speaking as an individual. So I'm pretty happy.
Thanks, Rod, and thanks again for the suggestions.
Anybody else in the room who has been keeping track of the draft have any comments to make? Okay, thanks. We'll ask for the last call on the mailing list to give people some time to process the draft. But also, my opinion as an individual is that it seems ready. There's no major comments coming in, so I think we can push it through. We'll issue the last call after this meeting on the mailing list. Thanks a lot, Mel here.
All right, thanks, guys.
Yeah. Hey, Colin's in the back of the room here. When we issue the last call for this draft, how long should we give people on the list for comments?
Hi, Colin Perkins. A couple of weeks is typical, unless there's a major holiday or something in the middle.
Sounds good. Thanks.
Right, thanks. And can we invite our last speaker, excluding the brief book pitch by Rod afterwards. Carlo, would you like to come up and share your screen? Or I can share your slides if you prefer that.
Can you hear me, by the way?
Yes. Or you can share the pre-shared slides as well. That's also an option.
Yeah, I will try that.
And can you speak up a bit because you're quite quiet?
Okay, I'll crank up the volume a bit. Is this better? Can you hear me well?
Yes, it's better. And if you don't mind, you can also switch on your camera.
Yes, let me share my slides first.
Yeah, your slides are online.
Can you see me?
Yes, go ahead,
Cool.
Carlo, now. You have 20 minutes.
Yes, hello everyone. My name is Carlo. I'm speaking to you from The Hague in the Netherlands today. I am a PhD candidate at QTech, TU Delft in the Netherlands, and I wanted to share with you a recent achievement that we have done in our group, where we try to demonstrate entanglement and some limited quantum communication applications through a quantum network stack. Let's see together what that is. We'll be looking at some background and what the goals were for our project, and briefly describe what we mean by programmable quantum networks and quantum network nodes. And I'll be sharing with you some details about the implementation of our system, and look at the results, most recent results, and briefly also some mention about the future work we have in mind. Just to make it clear, this presentation is mostly based on this article that was published last year in NPJ Quantum Information. So a big shout out to all my colleagues that made this possible, including Wojciech over there. And so let's begin. What do we want to achieve with this project, or what did we want to achieve? Basically, we have like a variety of implementations of quantum networks, but we'll mostly be considering entanglement-based quantum networks that generate entanglement through what we call a heralding mechanism, where there's a midpoint heralding station between your two nodes, and this heralding station communicates whether the entanglement attempt was successful to the nodes. So this is a brief mention, but it's important to understand a couple of things later down the line. And what we also know is that we have a variety of quantum network testbeds around the world at the moment. We'll be reusing one that's been also used for some demonstrations in our labs. And we know of a bunch of protocols for quantum communication, specifically in what we would call the data plane. So this is a given. What do we want to do? We want to be able to operate a quantum network, which is generally heterogeneous in nature. So there are many implementation of quantum platforms, and we would like to be able to control all of these seamlessly without too much knowledge, without requiring the user to have knowledge of the platform itself. The network nodes should be programmable in a way that, again, the user doesn't need to know what platform it runs underneath them, and the nodes themselves don't have to know what application we're going to run on them. So the code software that's running on them shouldn't be tailored to a specific application, like quantum key distribution, for instance. Ideally, right? And we also would like the resources of these nodes to be allocated according to some policies and demands that are dynamic throughout the operation of the network. I think this is fairly, we can all fairly agree on this, and I don't need to convince you on the importance of having programmable networks and nodes. But in the context of quantum networks, these goals and requirements mean a lot, actually. So I will try to map these goals onto a simplified view of a network and see which of these goals we try to achieve with this particular project. Some of them will be left for future work. So in general, an infrastructure of a quantum network looks like the following a bit. You have at the physical layer a bunch of quantum devices that might be implemented differently. They might have a different quantum platform, and this is indicated in this diagram as different shapes in these quantum device blocks. On top of which you have some generic control stack, hardware and software, that will be running your nodes. So first of all, given that the network is heterogeneous, you might see that you need some kind of layer. You normally call this a device driver at the bottom of your controller, which will make the interface, will realize the interface to the specific quantum device, so that whatever software stack you implement on top of that doesn't need necessarily to know anything about the underlying platform, ideally again. We also want these nodes to be programmable, which generically means that you will not be deploying some ad hoc software stack or application-specific algorithm, but more something like an operating system that manages the resources without knowing what applications are being run, only knowing that there are some applications being run on the node. Part of this operating system will also include our quantum network stack. And finally, if you want your network to be configurable, you might want to deploy some kind of control layer, control plane that, based on a global network knowledge and also maybe some more like a local area network demands, will deploy some kind of quality of service policies on each of the nodes, and also some sort of schedule that the nodes will have to abide by. What do I mean by a schedule? We'll see a little bit later, but essentially, for you to achieve heralded entanglement, you want the two nodes engaging in an entanglement attempt to be both doing something actively at the same time. To make it easy for you, and for the paper that we have written in our experimental evaluation, we have only focused on two nodes, and also just a subset of all these beautiful abstractions that I have talked to you about. Obviously, we have a plethora of nodes in the lab, but no, I'm just kidding. It was just a first step towards something like a global network, but all we had available at the moment was two nodes. But we still think it's a pretty cool result, and hopefully this will open up the door to more experiments. So a few details on our implementation. Basically, actually just one slide back, one moment. Again, our goal was to deploy some kind of rudimentary network stack on top of a couple of quantum network devices, and to run some simple applications, quantum networking applications. As for the network stack, we have taken things from literature. We know that a couple of 4 years ago, a first link layer protocol for quantum networking was proposed, and just 1 year later, a network layer protocol was also suggested. So we basically implemented these with a few changes. Most importantly, on this slide, one key objective that we had for our network stack in general was that the way or the timing that the two nodes would be following to generate entanglement would not be computed locally, or at least, or even like agreed by the two nodes solely. Because if you deploy these two nodes in a larger network and one node is connected to like multiple of them, we don't think it is fairly easy to for a node to compute a schedule without knowing what's actually going on the nodes that are connected to it. And if these nodes are also, they have more neighbors, this is the nodes you're considering. So at least conceptually, computing a network schedule with a global view of the network would be best done at the control plane. For our implementation, this control plane was some person manually computing the schedule, just to demonstrate the concept. So what the schedule looks like is a bunch of time slots with millisecond resolution. And each time slot tells each node what this node can do in this time slot, or specifically when it comes to entanglement generation, which of its neighbors or neighbor it can connect to in that specific time slot. Just be aware also that to actually generate entanglement, you need a very, very high level of synchronization between the two quantum devices. And this nanosecond resolution synchronization is actually delegated to the physical layer. So you only know when you'd like to start entanglement at the network stack layer, but then the actual trigger happens at the physical layer. We deployed our control stack on two nodes, and I'll actually gloss over this slide in the interest of time a little bit. But just remember, it is 2 nodes in a university lab, so just spaced by a couple of meters, not that much. And so we'll go into the evaluation of this. To summarize, the again, goals or applications that we want to run, these are very simple quantum networking primitives. Specifically, we try to generate entanglement at various requested fidelities. Given that the underlying hardware actually has this capability, you can ask for a certain fidelity in a range, and this gives you a trade-off on speed versus quality of the entanglement. And we'll be looking at also just like simple fidelity of the entangled state as the quantum performance metric, and the latency to deliver entanglement since the request arrives as classical metrics. We also ran a couple of more applications, but we're not going to talk about them today. At the application layer, we make use of this software development kit called NetChasm that basically lets you specify your application in a high-level language, i.e. Python. And this gets converted into something that the control stack can actually understand. So a bit more like kind of like an assembly code, but not really, just more low level. So for this particular application, what we're doing here is we're looping over a few iterations for statistics, then looping over a bunch of requested fidelities. So we can ask the physical layer for fidelity 50% up to 80% or something. And then we'll be measuring in various bases on the 2 nodes, which we call client and server here. So this is to do some kind of tomography on the entangled state. The body of the application looks like the following. The bottom 3 lines, basically, you create entanglement with your neighbor. You perform some kind of rotation to read in the bases you want. You measure your qubit, your end of the qubit. Looks easy, right? And it actually is. So this is one of the maybe hidden achievements that we wanted to share with you. You can easily program your underlying network or your node by writing a simple Python application at the moment. Clearly, the possibilities are limited by the hardware. So you cannot run whatever fancy application with more qubits than you have available, but whatever you have, you can easily code it up. And that's it, basically. I'll be sharing a couple of results. So when it comes to fidelity, as I said, we've requested fidelity, entangled generation at multiple fidelities, and usually achieved at least what we were asking for. So the blue dots in this figure show that we're able to deliver a entangled pairs at a fidelity which is almost always higher than the one we requested, except for fidelity 0.8, which is slightly below the requested fidelity. That's a great result. This is mostly dictated by the performance of the hardware itself. So yes, if your hardware is not capable of delivering any fidelity, then that's not up to your control stack, but at least given that our hardware is capable of doing that, we were able to demonstrate also with the software stack deployed on it. If we look at the latency for delivering entanglement, you can see that it is mostly dominated by what's happening at the physical layer, so the actual entanglement generation attempts. The higher the fidelity, the more attempts you need to achieve entanglement, clearly. And as you see, this the latency of the physical layer scales kind of exponentially with the requested fidelity. As you can see, also there's like a bit of a added latency overhead coming from we call it the link layer protocol here, but it's basically the workings of the network stack. And where is this coming from, actually? Mostly, if you're on the right-hand side of the slide, you can see that if your entanglement request arrives in the middle of a time slot designated in your network schedule, then you will only be able to start entanglement attempts at the beginning of the next time bin. This is for various reasons, but basically it is to ensure that both nodes are synchronized and start kind of at the same time without wasting entanglement attempts, which are harmful to the quality of other qubits that you might have in memory. And that was basically it. Was a fast run through, but we're happy to see that the more high-level software abstraction that we're building on top of the hardware both make it easy for the user to program their applications and also don't incur a detrimental overhead on quantum and classical performance metrics. A very brief mention to what we have in mind for the future. We're working on some rudimentary operating system for quantum network nodes to make the execution of applications even more powerful, particularly resource management and concurrent applications should be running without the user having to care about these aspects. We would also like to scale our experiments to bigger networks and study the node and network level scheduling a bit better, and eventually also come up with a design and implementation of a control plane for that network. That was it for me. I hope most of the things were clear. I hope you heard me. If you have any questions, please ask. Thank you for listening.
Thanks, Carlo. I think actually we do have time for a few questions, and I don't see anybody online, but Pete Resnick already pinged me, and Pete is at the mic.
Hi, this is Pete Resnick. If you go back to that graph where you said most of the values were above the target, it looked like exactly half the values were above the target and half were below.
Sorry, yes, I should have specified better. Thank you for your question. The yellow dots that say targeted here are slightly above the requested fidelity. So the gray line is the X equal Y line, and this is actually the request fidelity.
Thank you.
The yellow is
now
what
I
the
got
hardware. Okay, so the hardware is actually trying to deliver a bit more than you're requesting to account for these possible errors, actually. Yeah, sorry, didn't specify that clearly. Thank you.
I actually had a related question about this. So is there a mechanism for negotiating down if the hardware can't fulfill the request? And is there a trade-off between fidelity and rate? Is that expressible in your system?
Thank you again for the question. So there's not a systematic way to negotiate this at the moment, but there's ways of doing that. At the moment, we have, so the netcasm applications that we run over here, we write over here. They are sort of compiled down into some code that is specific to the underlying software stack. And if the compiler has knowledge of the physical platform and it knows that some fidelity cannot be achieved, then it should give you an error clearly. So this is just like the best way that comes up to my mind as to how to achieve this. You might want to have this dynamically configurable, or you want to be able to, I guess, negotiate this dynamically, but we don't have this at the moment. I think it would be something easy to do. And there is a trade-off clearly between fidelity and latency, or like entanglement generation rate clearly. This is not being expressed at the moment anywhere in the SDK or in the control stack. Is this something that the user programming the application probably knows? If they don't, there should be a mechanism definitely to inform them. But yeah, so the trade-off is It's also kind of dynamic in nature, depending on the state of calibration of your quantum hardware. You might have a certain fidelity latency trade-off or a different one. I'm not sure if one could specify some kind of average and give it to the user. I'm not really answering your question,
Okay.
actually.
Yeah, sort of. In the interest of time, Joaquin's got a question. Let's go on to Joaquin's question.
Great presentation. So this is just one clarification question. You mentioned that you need to compute the schedule of the network at the control plane. So my question is this, yeah, thanks for the slide. You have the big yellow time slots. My question is, are these time slots fixed for the network? And then you mean computing the schedule because you are trying to accommodate several users? Or are these time slots gonna change depending on who is arriving at the network?
Let's keep this short in the interest of time.
For sure. Thank you for the question. It is a very good one. I don't have a precise answer. There are people studying this, but potentially you want to be able to compute this as more nodes join the network and as the demand changes. Yes. So it shouldn't really be fixed, I think.
Okay. Okay, I can continue in the chat.
Sure.
Thanks.
Thank you for the questions, and thanks, Carlo, for speaking. We're now moving on to the last part of the program, and Rodney has something to mention about his book.
All right, I'll keep this real short. As those of you who are either at the hackathon on Sunday, or who are on the QIRG mailing list have seen, we have released a draft of our book to be titled Quantum Communications. Mikkel and I are working on it. Mikkel's in the room there. Wave hi, Mikkel. You can talk to either one of us about it. Next slide, please. So it's intended to be an undergraduate textbook. It's being released Creative Commons, CC by SA. Links in the slides there, which you can get from the data tracker. The Dropbox link to a PDF will be good for about a week. The GitHub link is permanent if you can compile LaTeX from there. We actually already have a pull request to improve automated building of the PDF. Thank you to BKM. I'm not sure who BKM is, but thank you for that. We'll get that incorporated soon. This is a companion to our online course that's already available on YouTube, and this was supported by the Japanese government QLEAP Education Project. We are also in the process of translating parts of these materials into, with collaboration from some people in Chicago, as well as other places. We're translating parts of it into Chinese, Arabic, French, Spanish, American Sign Language, Korean, and I think I'm missing something. Go on to the next slide, please. And let's see. So the book's about 300 pages, includes exercises. It is intended to be a textbook. We can use more exercises, so if anybody wants to create some, we would love to have them. Basic math background for this book is pretty minimal. The idea is that this would follow on from your first very low-level course in quantum information. But if you're really ambitious, you can work directly from this without any background in quantum stuff as well. All right, next slide. And let's see, that's the table of contents. Each one of those is a chapter. The online videos for each one of those are cut into short steps, but each one totals up to about 45 minutes. So the total of this is about 11 or 12 hours worth of video that's online, or the book is about 300 pages, as I said. Next page, please. And we are looking forward to having lots of feedback from you, either as issues or comments on the GitHub repository or via the Google form. And if you submit them via either of those, then they will get tracked and not lost. And enjoy it. And if you have any questions or comments, we would love to have them. And if you contribute enough to it, we'll put your name on the contributors page. That's it.
Okay, thanks, Rodney. So yeah, Rodney already wrote a book on quantum networking some time ago, and I learned my quantum networking from that, so I do recommend his works. And with that, that's a wrap for this meeting. Thanks everybody for attending, and looking forward to seeing you at the next QIRG meetings. Thanks all.
Yes.